Hello, everyone. Welcome. I'm Stephen W. Long, and this is The Writing Life. Today, my guest is Lee Mosley, and I'm so pleased to have Lee here. And this is a bit of a departure, and I'll explain that. So often, what I'm interested in is the technique of writing, the quality of the writing, maybe the author's procedure, how do they approach this. And all of those things would be true with Lee, with the addition of the fascinating subject. And it's something that I'm interested in. Obviously, lots of folks are. But it's a tough subject. And I was thinking maybe the advantage is, as the author, they can't prove you wrong, at least not at this point.
Well, I fear that perhaps they can prove me wrong.
All right.
In fact,
And Lee, before we get too far,
Surely.
Tell us, can you describe this thing in a nutshell? I mean, it's a small enough topic, right?
Yes, it only covers the entirety of physics as we know it.
Okay.
The issue with physics, in great part, is because we have a great deal of technical expertise. We know fairly well much about the way the world works and the way things work within the world. But there are some essential questions that have not been answered satisfactorily, and one of them, at the heart of everything, is there are two basic theories having to do with physics. One is relativity, from Einstein mostly, and the other is the particle theory or quantum theory of physics, and they just don't go together at all. Now, fortunately, the two theories are at almost two exclusive realms in the universe. Relativity on the one hand, large things moving fast, planets, stars, that kind of thing. And on the other hand, particle physics, which is the tiniest grain there is. So I flatter myself by believing I've got an idea that might help unite the two. And that's what the book is about.
Okay. And is it, can you summarize for us and give us a sort of a general thought, or do we need to get into the book?
Oh, I can do a general thought
right.
to begin with. So we know something about the fine grain of things. We know something about the way waves and particles behave and so forth. We know and have known for a long time about the range of energies that things can have. And there's been speculation ever since the Greeks about even such things as shape and form. So in Greek mathematical philosophy, the dodecahedron, for example, was the shape of the universe. And each one of the various planets and the realms of the planets were defined as triangles and squares and so forth. So what I've been able to do is find pieces, including some things from abstract mathematics that didn't had, so far as I know, no application in physics, and put them together into a model of what might be the tiniest structure within all of the physical world that would incorporate what some of the audience would know about brane theory and string theory.
Now, before you go on, brane is B-R-A-N-E.
Exactly.
Can you?
From the word membrane.
Okay.
Yeah. And essentially, although this is a gross simplification, there are strings, which simply are one-dimensional entities with ends that are called nodes, but no different, just the string that vibrates, and vibrates in space-time. From the mathematics of a vibrating string, the theorists have been able to come up with a description that will fit virtually all the subatomic particles and the forces that they are affected by. The mathematics is far beyond any normal human being, and typically takes decades to learn. And you and I are normal.
We're normal.
All right. We're trying to be normal.
All right.
But the theory there is when you ask a physicist to describe string theory, they'll walk to a blackboard and they'll make a little wiggle. And they'll say there's a string. It's floating in space, moving around. And because of its harmonics, its vibrations, and its contraction or expansion, it describes virtually everything we know about the physical world in its subatomic particles. And the strings can even loop around, so they can become little rings of themselves. They don't actually describe everything, though, and that's a problem. So another group of physicists, mathematical physicists, said, well, let's take the strings and iron them out so they become a membrane, hence brain theory.
All right.
And now we have a thing which has two dimensions. It has width, say, and length.
Okay.
And now you're talking about a vibrating membrane, which mimics some of the things we know about the world. So the combination of string and brain theory was recently made, and they explain yet more, but they don't go everywhere. And a big problem with those little entities is that they still float around in space-time. Space-time is like a backdrop. And so if you have a theory that doesn't describe maybe the single most important thing going, which is the fact of space and time itself, then you've got a theory that's not complete. So you're able to describe a great deal of the world and do it wonderfully well, but you fall off the edge of the Earth at some point. And my theory here, and in fact the picture on the front, shows a dodecahedron,
Okay.
which to my mind, and I'm way simplifying all of this, combines strings in the edges and brains in the faces in a single entity. And
Lee, this is so complicated, at least
Surely.
it is for me. So is this an analogy, or
No.
does it? No, this is
in my proposition,
a physical thing.
well, yes, let's say it's a physical
All
thing.
right.
And I can get into a bit more here, and I hope I won't lose people, by saying that, well, there was a fellow named Max Planck in around the 1900s who was looking at a particular problem, and in looking at the problem, he determined that there were some minimal vibrations that things could have. It couldn't get any smaller than that, and it's a measure of heat and energy. He determined from those measures the smallest thing something could have, the smallest size a thing could have, called the Planck length. If you have length, then you can make a volume, so he then described the Planck volume as the smallest. So now you had a small energy and a small volume. He worked with Einstein about what was called vacuum energy, which is the minimal energy available in space at any particular point. So if we have a volume and we have an energy and we have, let's say it's a ball now. Well, it's a ball, very small, but that can't be the entire universe. So if space is subdivided into such things, then they'll pack together. And when they pack, they can't stay balls because there would be gaps between them. So they crunch together like a honeybee's comb. A honeybee doesn't intend to make a hexagon when it makes a cone. It just pushes in all directions, and the other honeybees pushing the other directions end up flattening the walls, and they make a honeycomb. Same thing here. The fun for me was when I discovered that two mathematicians working on an abstract problem that had been around for a long time. What happens when you take equal pressure, equal volume entities, and you mash them to the point that they have no space in them between them anymore? What shape do you get? And Lord Kelvin, who's famous for his temperature plus a bunch of other things, surmised that it would be hexadecahedra, which is a very complex polyhedron like this, mashed together, and it would work. But two fellows named Weir and Phelan in 1993 determined that wasn't really it. They got a computer model. They used a form of what's called an A15 configuration of metallic clathrates, which I'm sure everyone knows about.
I hope we're scrolling something across the bottom here.
But anyway, so they determined, well, yes, compressed bunch of these little orbs of energy would make a polyhedron, but it wouldn't do exactly what Kelvin said. It would do better. It would make about 12 dodecahedra tetradecahedra and about 2 dodecahedra in a little wad. And interestingly, those little wads would do what is called in mathematics, they would tile, just like a tile floor. So if you have one, and you can put another one on, and another one, they just click into place. So suddenly you have a basis for something that could fill all of space, be made of things that are tiny, 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 would have the vacuum energy, and would be of themselves. And fortunately also for me, and I hope for the world, the lines, the edges of these little fellas would act like strings. The faces would act like brains.
Sure.
So now I've found a way to come up with a minimal thing with a minimal energy and a maximum energy too, according to theory, that has the characteristics of strings and brains and occurs naturally. And this is something that no one has speculated on yet. So I didn't do the math. I didn't do much in the way of breakthrough. I just took a thought here and a thought there and put them together in a new way that I believe. I've never seen anybody write anything about this.
Yeah. And then this bridges the gap between particle physics and general relativity?
It does, and here's how it does the general relativity, because up to now I've been talking about characteristics related to particle physics. The biggest problem between relativity and particle physics is that relativity has a great deal to do with gravity and the speed of light and that kind of thing. Well, there are 4 forces that we speak of these days. There is the electromagnetic force, there's a force within atoms called the nuclear strong force, another force within atoms called the nuclear weak force, and those are all well described in field theory and in mathematics as a kind of an electromagnetic phenomenon. Nobody knows what in the devil gravity even is.
Mm-hmm.
We know what it does. If you're this far away from something, it's going to have a certain gravitational effect. And if you're this far, it's going to have a quarter of that gravitational effect because you've doubled it, and that's the way it works. We don't know why, and we're not even really sure how the sun can pull the Earth, if that's what it does.
Mm-hmm.
We know it does, but what is it between the sun and the Earth that has any attractive effect? It's like voodoo, but it's voodoo we know. We have the math for it. We have the applications. We can put something, we're planning to put something, another orbit around Jupiter. We're going to put people on Mars. We work with this all the time, but we don't know what causes gravity.
It's a predictor. We can predict it. We just don't understand it.
And so that's the problem in physics and in a lot of sciences. We can describe a thing pretty well as to what it does, but we don't necessarily know why it does it that way. So a correlate to this is inoculation. So when hundreds of years ago, people were getting sick and dying of disease, and all they knew was to keep people away from people, quarantine, until the disease pretty well burnt itself out in a population, and then people could go back their lives. But when the discovery was made, perhaps accidentally, that people who were closely associated with the animals that got sick either got sick themselves or lived, then the idea of taking the pustule from a cow that was infected, scratching somebody's arm, smearing some of that on, and waiting to see the result, ended up with a wonderful outcome. People might feel badly, the site might swell up, but mostly they got a very mild form of the disease, and then they got better. So they knew what to do but they didn't know why. The whole idea of the immune system, or for that matter, even bacteria or viruses, was unknown in those days. So they made a discovery, and they worked with it quite well, just like we've made plenty of discoveries in physics and work with them quite well. But we don't know what causes gravity, which gets back to your question. If you take a shape like this, and it's made of strings and brains in a form, and you excite that shape, it's rather like exciting a guitar string. So a guitar string is connected between 2 points. If you strum the string wants to move this direction. Because now it's moving this direction, it actually exerts some pressure to pull in on the 2 points. Now, a guitar is not going to do that. So the string itself actually has to stretch somewhat. But if the string were not firmly attached and were in fact rigid, and you strummed it, what it would do is draw in the 2 ends. And it would draw it in proportionally to the vibration or the energy in it. So we know, according to Einstein, that mass and energy are the same, EMC squared. We also know that when you add more energy, you get more mass. And so let's take one of these shapes and let's add energy in the form of light, heat, whatever. Everything is more active. Just like the string, it tends to draw in. And I'm saying that that drawing in not only adds mass and energy, but it also shrinks things. It shrinks space. And that shrinkage of space is what, I'm getting a frog in my throat, is what is mostly described as being gravity. So
Oh, that's interesting.
when people talk about how gravity works, they often use an analogy of a rubber mat. So you stretch it out, a rubber membrane, you put a cannonball in the middle, it dimples down. Then you take a marble or a BB and put it over here to one side. Now the marble and the BB also push down a little bit. They make a small dimple, not nearly what the cannonball does. But if you spin the marble and BB around the thing, it will eventually fall into the gravity well of the larger object. So we know that space shrinks because gravity and energy impact. What we don't necessarily know is how that happens. And this is how I think the nexus of my theory and these others fit well with relativity.
Mm-hmm. Brought you.
Thank you. If this is true, then we have not only a way to define gravity within this, but we have even niftier a way to define quantum gravity. Because up until now, gravity on the one side has been pretty smooth, considered to be that way. But the world on the other end of the spectrum in theoretical physics is a quantum world in which things are chunked. And if we're going to unite the two, we need to find a way to put together chunky gravity. So it needs to be in stepwise fashion. You can't have 8/10 gravity, 9/10 gravity, 10/10 gravity, subdivided so smallly that it just becomes totally smooth. At some point, it has to become stepwise. And this is also where these little fellows come in. You see, if you have a volume, take a sphere, and it has a harmonic of vibration inside it, that vibration is going to act like water in a pond. It can't have all the various waves, but it can have some waves that reinforce each other and other waves that destroy each other. So you get the waves that are reinforced at a particular frequency, but not at the middle frequency, the half a wave kind of thing. So if you have a volume that can only contain waves, in this case emanating out and back in again, that are in a harmonic, then you have a stepwise kind of process.
Oh.
Now, those waves then create a pressure or in some cases, tug in, and they will then have to do that bits and pieces at a time, rather than simply smoothly, because the waves would clash with each other. So now we have, in this model, a quantum gravity, space collapsing. Interestingly, though, the way this works is that gravity doesn't pull. If space collapses in, so it makes a bit of you, you've helped collapse a bit of space-time, actually quite a lot of space-time, because these things are small.
I thought you were commenting on my weight.
No, and so long as we don't comment on mine, we're in good shape. The thing is that if you have a bunch of bubbles and they all have the same pressure, then they're all going to be about the same size. But if one gets more massive and shrinks in, then the others around it have less pressure, have more pressure on them. This one's having less pressure now because they're not pushing out as much. The others have relatively more pressure. They're kind of pushing in. So I'm saying that if we have a situation where we're making a dimple in space-time like this because little pieces are collapsing in with themselves, then we have a description of gravity that's not gravity pulling you. There's no doe-eyed kind of allure going on, but it's really that the other parts of space-time, which are still large and puffy, kind of push you in. You don't feel that any more than you feel gravity pulling you. When we say that we feel, heavy or weighty
Sure.
or whatever, what we're really feeling is where the floor stops our feet or the chair stops our bottom. But if a person's falling, they don't feel gravity. In fact, they're weightless. It's when you hit the ground
Right.
that you notice just how much gravity there was being exerted. And so here, we wouldn't feel the exertation of the pressure of space-time on us any more than we would feel the pull. And so it works, and it works even mathematically. As a matter of fact, there's rather a lot of math having to do with how gravity behaves, such that you can even calculate, as I have in the book, a mathematical formula for the amount of gravity in the bowler that you wear. So space has a certain amount of energy. That energy converts into a certain amount of gravity spread everywhere, because energy is rather like mass. So the whole thesis of the book really is to take all the various pieces that we've learned and know all along, relate them to the Weir-Phelan structure of dodecahedra and tetradecahedra that tile together and create, I believe, all of space-time. And I haven't mentioned time, but these also explain time as well.
Mm-hmm. I actually wanted to ask you, we've got a little time ourselves, but
Yeah.
so I want to get this in and then we'll come back a little bit.
Certainly.
You're going to have a signing?
I will.
And a book sale. Can you tell
The
us?
signing is on the 21st. It's at the Golden Valley Brewery,
Okay.
and everyone is welcome to come.
Okay.
I would be overjoyed. I'll have books there, and I'll be doing a
And
little.
what time?
It's at 6 o'clock to 7:30,
Okay.
and it's if you want a meal and something to drink, you're welcome to purchase it.
Okay.
If you'd like a book, you're welcome to purchase it.
Okay.
And I'll be glad to sign the book and do I hope, maybe even a clearer job of explaining all this.
Well, it's, I had the same feeling when I read A Brief History of Time.
Mm-hmm.
And that is, in the moment, I'm shaking my head and thinking, I think I get this.
Yeah.
Now, when I walk out the door, I don't think I could repeat it. But it does, the things that I understand about this and the way that you present it, at this moment, at least, it makes sense to me. So, get back to the physics. Does your pulling together of these various bits, does that address dark energy, dark matter, multidimensional universe?
Actually, all of those things.
Okay.
Without fumbling around in the book, I have, I don't know, 11 or 12 of the truly basic problems in current physics, and among them are dark energy and dark matter, the nature of time, the nature of gravity, the nature of space, plus lots more that you mentioned. And I come pretty close to answering every one of them. A problem, and I have a book here called The 4% Universe that I've referred to on occasion, not here, but within the book. With dark energy and dark matter, we discovered somewhere around the second Clinton administration that we only know about 4% of the entire universe, that we've detected effects of about 27% of mass out there that we didn't know about at all in the universe, and about 62 or 3% of dark energy that we didn't know about at all. And that adds up to 100%, so it can't be quite that. But anyway, we have roughly about 4% of the universe that we can even see and measure. The rest of it is dark. Well, in my formulation, it's not. It's true. We don't see it, we don't measure it. We see effects of it, we measure effects of it, and we speculate on what that is. But if space is simply and only divided into many, many billions upon billions of tiny bits of energy, they don't have to do anything most of the time except be there. And most of the time, that's all they do. Space is mostly empty, and what isn't empty is mostly filled with gas and dust. That's about it. But if you have enough of that, it's doing things, it's interacting with each other, each piece with each other. And I think that's really where the dark energy comes from that blows out the expansion of the universe. I think that's also where the apparent mass comes from that causes what looks like gravitational effects when we don't see anything there. It's space idling that just minusculely, but over great distances, comes in a little together, not making anything. Comes out a little together, not blowing anything away. But it's got native energy. And just in the past couple of days, there have been some articles published about how just this tiny fluctuation, this very rapid wiggling between one state and the other, is likely going to be helpful in explaining a great deal of this. And this to me is delightful.
It's delightful to me. And again, I suppose it's clear that I don't understand a thing about this, but that doesn't stop the enjoyment of asking the questions and learning what I can understand. So I just want to encourage everybody, if you have any interest at all, come to Golden Valley Brewery. Is it the 22nd?
21st.
21st, sorry, at 6 o'clock.
At 6 o'clock.
And
I'd be happy.
Come meet Lee. Maybe you'll be able to understand this a little bit better than I do.
Well,
but I look forward to the book.
And the book has cartoons and jokes.
Cartoons
it's
I can
lightweight.
Get.
Yeah. Yes, there are formulas. I even give people permission to put their thumb over the formula and just read the text if they want to.
Well, we'll do that.
So,
well, Lee, thank you so much.
Well, you're welcome, Steve.
Appreciate it. We'll get you back here when we have a little history under our belt and see how this goes.
Yeah, I'd like to talk with you sometime about the challenges of writing a technical book as opposed to, let's say, one that's
and that's more
creative.
What I generally look at is technique and so on. So, all right.
Super.
Well, thank you. All
Well,
right.
thank you.
Yeah. Thanks everybody for watching. Do come back if you want to contact me. StephenWLong.com. Suggestions, comments, and I hope we see you next time on The Writing Life. Be well. Thank you, Lee.